Hi, good morning, everybody. So it is my distinct pleasure to introduce Quinton Lawton, who is a fourth-year PhD student advised by Sharon Majumdar. Quinton holds a BS in meteorology from Texas A&M. During his time at Rosenstiel, Quinton has collaborated with researchers at the National Center for Atmospheric Research, the European Center for Medium-Range Weather Forecasts, and the NASA CPEX CV Field Campaign in Cabo Verde. On campus, Quinton has led the Canes on Cades Hurricane Outreach Group and was awarded the Outstanding Outreach Award in 2022. Quinton will defend and graduate next year. Quinton, thank you for being here today.
Hi everyone, thank you so much for that, Aiden. So before I get started, I want to just thank some of my collaborators who, without this work, it wouldn't be possible without their contributions. So Rosa Maria Squarios and Rebecca Emerton and Linus Magnuson have all been really helpful in some of the work that I'm about to show you. And I'm just going to kind of give you, this one didn't work. All right. So just to give you an idea of what I'm going to talk about today, I really want to first start out by giving you what I think is kind of a thorough background on what you need to know about what I call convectively coupled Kelvin waves, and focus on the general motivations of why we want to study these phenomena. And then I'm going to get into some of my old research or some of my early work here in that section. But for most of this talk, I really want to focus on some of the new work that I've been doing and that we've been doing on numerical simulations. And in particular, using these simulations to study the wave interactions that can arise in places like the Atlantic and how that impacts predictability. And then we're going to conclude again with some motivations for future work and what I think is, kind of the next step for this area. And so the background here is, why should you care about Kelvin waves? And why should you care about the interactions as they're represented in models? And so I'm going to do this. There's a very nice motivating case here. This is I actually gave a talk at the National Hurricane Center and I asked them, do you remember Tropical Storm Kirk? And no one did. So this is not a very well-known storm, but it was a very interesting storm. So Kirk was this tropical storm that underwent a brief, what we call tropical cyclogenesis or formation in the Atlantic Ocean back in 2018. And it was very brief, but what was really interesting was this happened after the passage of one of these convectively coupled Kelvin waves, or what we call CCKWs. And what's really interesting, this is just an animation of Victor showing kind of its, Kirk. Its messy organization, but it does eventually become a tropical cyclone. And what was really fascinating about this to me was the National Hurricane Center's predictions of this particular system. So if you're familiar with the Hurricane Center, they put out these 5-day, and actually now they do 7-day tropical weather outlooks where they look at the probabilities of genesis or formation in the Atlantic. And this little region right here was what eventually became Kirk. And 2 days prior to genesis, they were only giving this area about a 20% chance of formation in 5 days. 1 day prior to formation, that got bumped up to 30% in 48 hours, but 60% in 5 days. And within 24 hours, we had the formation of Tropical Storm Kirk. And one of the potential causes of this could have been the passage of one of these Kelvin waves. And this is an older animation, so what you're looking at here is basically the Kelvin wave signature is in this green area. And it's really hard to see on this screen, but there's this African easterly wave in this little dot that goes and passes this Kelvin wave. And right after passing this active part of the Kelvin wave, it undergoes genesis. And so this is something that we've seen in a lot of previous work and my work, and that these Kelvin waves can impact things like hurricanes. So I'm going to give you some background on the two main waves that I really study here in this work. The first are these waves called African easterly waves. These are these disturbances that move off of Africa, and they end up becoming oftentimes the seeds for tropical cyclones. And this is just an animation here that shows one of these African easterly waves from a few years ago that eventually became, in this case, Isaias, which just missed us here. But this actually originated off the coast of Africa and eventually became a tropical cyclone. The other wave, which you're probably less familiar with because it's not something we talk about day to day, are these things called convectively coupled Kelvin waves. These are eastward propagating waves, so these are waves that are trapped along the equator, and they produce these circulations that either enhance or suppress convection in various phases. And so these are pretty large systems. So this is just an indication, this is an animation of kind of the spread of one of these Kelvin waves. So this blue area is an active part of the Kelvin wave. And so you can see that they tend to ride along the equator going west to east, and they can extend, somewhat, over a few thousand miles, at least in their wind structure. And what do these Kelvin waves actually look like in the vertical? Well, this is a diagram showing the what we call an idealized structure. So if we had a Kelvin wave and we didn't have the pesky moisture that we tend to have in the atmosphere. So what we're looking at here is actually a y-axis is height in the atmosphere, and this is the Kelvin wave. And we see that in this part of the Kelvin wave, we have rising motion, and we have basically converging motions near where this rising motion is at the bottom and diverging motions aloft. And these lines indicate temperature perturbations. So in an idealized framework, these tend to be just wind and temperature-driven phenomena. But in the real atmosphere, obviously we have this thing called moisture and convection. So if we look at a real schematic, this is from observational data of a Kelvin wave. We're actually plotting the zonal winds. So what this is showing us is that there's winds coming in near the bottom, winds going out aloft. And one thing that's a little different about Kelvin waves in the atmosphere is not only do they have convection associated with this rising motion, but they also have a somewhat tilted structure. So as you go to the west, there actually is a westward tilt with height. And again, one of the reasons that this is important is because these waves are intrinsically connected to convection. And so there's something called convective coupling in the real atmosphere. Basically what this means is that because there's rising motion and there's also dynamics in play rising from rainfall, we actually have this intrinsic connection between the motions of a Kelvin wave and its convection. And one of the reasons this is important is that this often slows down the Kelvin wave in the real atmosphere and also can contribute to its amplification or the other direction, its dissipation. And numerical simulations are just well known to struggle with this convective coupling, and this will motivate some of the later work. So this doesn't really tell us why we should care about Kelvin waves. One of the main reasons we should care about Kelvin waves and easterly waves are that they contribute a lot to rainfall. So what this is showing is basically the average contribution of various wave types to rainfall over Africa. And so this top line here basically represents African easterly waves, which by far drive most of the rainfall over Africa. But coming in second place are actually these convectively coupled Kelvin waves. And so these are obviously very important for dictating rainfall in the tropics, and that has, of course, a lot of implications. One thing that we've started to figure out, both in previous work and some of our work, is what I showed you earlier on, which is that Kelvin waves actually impact the likelihood of tropical cyclogenesis. These are figures from two separate studies, one from Carl Schrack in 2015, one from our paper last year, that basically show that there's a favorability of tropical cyclogenesis is enhanced in a 1 to 3 day window following the active, convectively active part of the Kelvin wave. And so these Kelvin waves seem to affect genesis, and we don't really know why. At least we don't know the relative contributions of why. And so there have been a lot of theories on this, and I'm just going to briefly go through some of them. So there's this one theory that these Kelvin waves can affect basically just the large-scale environment in the basins like wind shear, moisture, that make in certain phases of the Kelvin wave these tropical cyclones more likely to form. There's also this kind of idea that Carl Schrack studied, which is that maybe these Kelvin waves, because they have these wind perturbations, maybe they're actually adding to some of the spin or the vorticity of these African easterly waves, and maybe this could enhance the formation of tropical cyclones, and maybe they also could enhance the outflow aloft to help the tropical cyclones. And that's kind of what this diagram is showing, is that these Kelvin waves could be adding to the vorticity to the north where the tropical cyclones tend to be. This isn't really satisfying to me because we know that Kelvin waves are really driven in the real atmosphere by convection. And so something that we've been working on is looking at how these Kelvin waves impact the processes we know are important for hurricanes. And so some of these processes include something called convective aggregation and environmental preconditioning, which I'm going to talk about later. But basically the summary is that Kelvin waves have this convective signature. They have a moisture signature. And this could contribute directly to these processes that lead to hurricane formation. So we've looked at this previously, typically in reanalysis data and satellite data. And so you may be wondering, well, how does that work? Well, I'm going to actually take a step back and talk about how tropical cyclogenesis works. So this is a diagram basically showing this process that people like to call environmental preconditioning. So this is a composite. On the right side of these is the time of genesis, and we've composited over hundreds of these easterly wave cases that became hurricanes. And one thing that we've shown that agrees with a lot of previous studies is that there's this increase in the convection and the humidity around easterly waves prior to the formation of tropical cyclones. And this kind of connects with this idea of preconditioning, that you need to take the easterly wave, make it a lot more favorable in terms of moisture and convection to forming a tropical cyclone for it to actually happen. There's also this idea that's been kind of tossed around, and you may have seen a little of this in Brian Soden's talk a few weeks ago, this idea of convective aggregation. And what this is basically the process of organizing convection from being this real scattered phenomenon to being concentrated near the center of a incipient disturbance that becomes a tropical cyclone. And one way that people have kind of proxied the variance of this convection is through something called moist static energy. And so what basically I showed here, and I showed this in a previous talk too, is that if you have a box, if you take the moist static energy or the convection and you aggregate it, you actually increase the variance of this box. And by increasing the variance of the moist static energy, we're able to actually build a budget around the variance of moist static energy. And so a lot of people have shown that this is a scary looking equation, but what it's telling us here is that the change in the variance of moist static energy is connected to some of these source terms. And one of these source terms is what we call surface to atmosphere enthalpy feedbacks. That's basically the transfer of those moist flux, from the ocean to the atmosphere where there's already convection. And also this long wave feedback where you're adding clouds, and this long wave feedback term where there's already clouds. And so this has been shown to potentially help convection centralize. And so what we see in tropical cyclogenesis, this is a diagram again looking at composites of tropical cyclogenesis, where genesis is on the right and we have pregenesis on the left. We see that there's this big increase in the long wave radiational feedbacks, that red line, in the 2 to 3 days prior to genesis. And the takeaway here is that this convective long wave feedback, is not just shown by our work, but other idealized studies, could be important to hurricane formation. And so I'm going to bring this back into Kelvin waves, because one thing that we've shown about Kelvin waves is that Kelvin waves, so now we're looking at Kelvin waves, now we're looking at what Kelvin waves do to African easterly waves. So this is the easterly wave averages as we look in the vertical. We're looking at diabatic heating, which represents our convection. And so on the right is the easterly wave before, and the left is after that active phase of a Kelvin wave. What we see is that the Kelvin wave actually increases the diabatic heating and also the convective coverage in and around easterly waves. So Kelvin waves actually make easterly waves have more convection, and have convection that's more widespread. And one thing that we sort of inferred or looked at was that these Kelvin waves, if you look at a Kelvin wave on the day 0, after the passage of a Kelvin wave, you actually see in the easterly wave, these long wave radiational feedbacks will tend to increase when we have genesis. So the idea here is that Kelvin waves could be adding convection, adding moisture, and by doing so, they're actually directly affecting these feedbacks that lead to the preconditioning of the easterly wave and also the aggregation of its convection. So that sounds great, and it's a nice theory, and it's what I like to think that it might be true. But something's really hard about looking at this framework. And one of the hard things about this is that it's really hard to assess causality. So it's really hard to say that this is happening not because of genesis, but because of the Kelvin wave. And so even though we have some of these takeaways that convections modify convection, that they modify moisture, that they're connected to genesis, and that this could be one pathway, the caveat here is that the data using reanalysis data, like I've shown you, or satellite data, we're just not able to directly connect that to genesis. And this kind of brings us into the modeling world. So one thing that I was thinking about was, is there a way for us to use a modeled Kelvin wave to assess, this connection? But one thing that's unfortunate about modeling is that models really, really stink at Kelvin waves. In particular, the convective coupling of Kelvin waves. So what I'm showing you here is a article that came out last year looking at the GFS forecast system, one of our main operational models, and we're looking at the skill at predicting a Kelvin wave's convection. And this is hours out of the forecast. And effectively what they showed was that there's no skill after about 2 days. It's a little deceiving. The UK Met showed skill out to 6 days, but that was primarily in the dynamic fields of the Kelvin wave. And so we're just really not able to simulate Kelvin waves. So there's another question here, which is, well, we can simulate Kelvin waves, but not for very long. And if we're not able to simulate Kelvin waves, are we able to simulate these interactions, which I showed might be important for hurricane formation? So this really just kind of naturally brings us into the modeling room. And that's what I'm going to spend the rest of the talk really focusing on. And so the big question here is, can we learn something? And in particular, what we're going to try to do is to modify the Kelvin waves in simulations to see if we can, by changing the Kelvin wave, we can change what happens with the interaction that Kelvin wave has downstream. And so the two main questions here, which is basically, are we representing these Kelvin waves, their coupling, their interactions correctly? But also, are we able to potentially use this to attribute some of the changes to easterly waves to Kelvin waves? For example, if we have a stronger Kelvin wave, do we see a stronger response in the easterly wave? And of course, the big picture goal here is all about global forecasting, because we want to try to improve these easterly wave and rainfall forecasts over Africa, TC forecasts over the entire globe, and also we want to have a better understanding of how these big waves, these Kelvin waves, can impact these very small processes that result in hurricanes. So that's kind of the motivation for the modeling that I'm going to talk about for the rest of the talk. I hope the modeling doesn't bore you too much. I have some really fun animations to keep you awake. But first I have to talk about how we actually model these waves in these cases. And so we're actually going to use this model that's been, kind of new model on the block sort of thing. This is called MPAS, the model for prediction across scales. It's being developed by NCAR right now. Still kind of in its infancy in a lot of ways, but this is a really neat model because, as shown on the figure to the left, it has this real nice like honeycomb-like mesh. So what that means is that you can actually change the size of your mesh. You can stretch the resolution without having these hard boundaries between areas you really want to focus on and the rest of the globe. And so it's really designed for these multi-scale problems, which is exactly what we're trying to look at here, the Kelvin wave and its impact on smaller scales. It's also been historically very good at simulating Kelvin waves. This is a study that was done a few years ago looking at basically the variance of precipitation in observations versus the convectively, the resolved or the high resolution MPAS versus the parameterized MPAS. And we see the Kelvin wave bar here stays about the same, so the implication is it's probably pretty good at Kelvin waves. There are other studies that have shown that it's pretty good at individual cases. What I'm going to show you today might actually fly in the face of that, but I think that's okay. So that kind of motivates the use of this model. And then, of course, we need a case, because what we want to do is I want to simulate a real case. I don't want to use an aquaplanet. I'm not going to use an idealized framework. I want to use a real easterly wave, Kelvin wave interaction case. And so the case that we're going to use here is this storm called Tropical Storm Victor. This was another one of those storms that no one at NHG probably remembers. Maybe they do. But this case is, again, over the open Atlantic, so it was a pretty nothing storm, but it also underwent genesis right after a very strong Kelvin wave. It was chosen because we wanted a strong Kelvin wave that the model could resolve. It doesn't quite do that, and I'll explain why. I'm going to kind of skim over this slide, but this is for those people who think about Kelvin waves a lot. One thing about Kelvin waves are it's really hard to just see the signal with the naked eye. We often have to use methods to isolate the signal. And so we, for this particular study, I just want to kind of confirm that what we do is pretty robust. We actually tried 3 different methods of identifying Kelvin wave signals, and they gave us about the same results. But for those of you who care about this a lot, one thing that we use is this fast Fourier transform method, where you basically pull out the Kelvin wave signal in space and time. So you isolate that signal so you can see where the Kelvin wave, what might be the Kelvin wave. That could be pretty narrow for these short simulations, so we also tried just a broad east and west filter, where you separate those signals going to the east and those going to the right. That's another method we use. And finally, there's this whole different way of doing things where you actually use a spatial projection onto the parabolic cylindrical functions. And that sounds really complicated, but basically what you do is you have this idealized Kelvin wave from shallow water theory, and you just project your model, your output signals onto those your theoretical solutions to see how well it matches, and that gives you sort of the PCF filtered signal. So again, this may go over the head of a lot of you, maybe you're not interested, but what I did was I used a lot of different methods and found them to be pretty robust. So back to Victor. What happened with Victor? Why do we want to use this event? And what we do here, I'm actually showing this progression, the genesis of Victor. So this projector, it's not as easy to see, but this blue area here, that is the Kelvin wave. It's in standard deviations from climatology. So this is looking at real data. And this Kelvin wave over the 24th of September through the 30th propagates across the Atlantic, passes an easterly wave, and that easterly wave, which is right here, becomes Tropical Storm Victor. And a fun fact, this was actually the second strongest interaction in my 4-year database that I used for previous papers, so we thought, well, MPAS should do pretty well with this. A lot of foreshadowing here. So in addition to the Kelvin wave over the Atlantic, what's kind of nice about this time period is we had a lot of Kelvin waves around the globe. So this is a Hobb model diagram showing longitude, so we average signals in latitude, and it shows kind of the progression from west to east of these Kelvin wave signatures, these negative values. This is filtered brightness temperature, so this is showing you the convection right here. And so this very strong Kelvin wave in observations, that is our Atlantic Kelvin wave. It's, again, incredibly strong, over 3 standard deviations, actually 4 here. But you also have a number of other waves, so this gives us some nice comparisons to look at. And we'll be focusing a lot on this Indian Ocean Kelvin wave later on. All right, one last thing. So how do we set up these simulations? Well, we're going to initialize them on the 24th. We're going to run 8-day simulations, okay, yeah. But one thing we're going to do here is have a set of controls. So one of our simulations is going to be what we call convective resolving in the Atlantic. So we're going to have a 15 to 3 kilometer mesh where everything outside of the Atlantic is 15, inside the Atlantic is 3. And then we're going to have a set of 30 kilometer just course runs where we parameterize, we don't directly resolve convection. This is just showing us the percentage of each of these models we ran, its resolution of convection. So the high res in the Atlantic resolves about 90% of it. And then what we're going to do is we're actually going to either amplify or dampen the Kelvin wave at initialization and then run different versions of these controls. We start out doing this in 30 kilometers for computational reasons, but we're going to expand this later. And we're going to modify two different ways. One way we modify is we just we pull out the wind signature, we modify that. Another way is we just modify that plus the temperature plus the humidity. And so we're going to compare all of these. And so the method for modifying these is pretty simple. We're going to use we initialize this with the ECMWF's IFS output, which I can get into why we do this later, but effectively, it seems the MPAS seems to work a little better when you give it IFS versus the reanalysis data. And what we're going to do is we're going to filter 1 month of this data and at all model levels, and we're just going to basically find the Kelvin waves by filtering it, and then we're either going to add or subtract that to the initialization. And so this is just an example showing you basically the different simulations. The top rows are the amplify minus the controls. So that's the cases where we amplify the Kelvin wave and subtracting out the controls, showing the differences. We can find this to the tropics, so we do 20 south to 20 north. And we do the same thing with the humidity and other fields, depending on which experiment we're running. Okay, so I've gone a lot into the background of this, but I just want to reiterate here that we're trying to modify this at initialization, and we're primarily going to focus on the course resolution simulations. And we're going to have a high res as kind of our control for the model. And we're also going to pair with the controls. Okay. So here's a pretty picture. This is that high resolution where we have a convective resolving mesh in the Atlantic. It's just showing the progression of surface fields. On the right, we have the simulated radar. On the left, we have surface winds. You have surface pressure overlined and kind of a bunch of stuff going on. Basically, this is to show you that in the high-res run, we have this really nice Kelvin wave moving off the coast, African easterly wave moving off the coast, passing a Kelvin wave and then becoming a tropical cyclone. And when we look at the 30-kilometer runs, it's a little more less interesting. It's hard to know if it actually went through Genesis, but we at least have a strong Kelvin wave, so this kind of plays into some of the differences we'll talk about later. Okay, but you're here, you probably care. What happened with the Kelvin wave? So what we did, we went in, we changed the Kelvin waves. So what I'm going to show you is a figure that looks complicated at first, but we're going to break it down. So what we're looking at here are 3 time shots of the filtered wind, which is the contours, and the divergence, looking in the vertical along the equator. So this is giving us an idea of the winds of the Kelvin wave. And on the left-hand side, we have the 25th, and we go through the end of the simulation. And I just want to highlight here that at the upper levels, we have this divergence and convergence kind of couplet. That's the upper level signature of, in this case, this is in the Atlantic. And then we have this Kelvin wave over the Indian Ocean, which is actually a lot stronger in terms of the divergence in the wind, and also extends further down into the lower atmosphere in the simulations. And these, propagate towards the east. What I'm showing you right now is actually the run where we amplify everything. So we take everything and change it in the initialization. So I'm going to just thumb back and forward between the control and where we dampen everything. So now we're going to go control, dampening everything, back to control, amplifying everything. So I hope, if you see the colors, we see that all of this, a lot of the signal gets actually modified. As we dampen the signal, we actually remove a lot of that initial divergence, and that actually stays true throughout the simulations. And I'll show you a diagram that kind of summarizes this. So we are actually able to modify both the upper level Atlantic Kelvin wave and the Indian Ocean Kelvin wave by changing things in initialization. Good start, right? So this is the velocity potential. I didn't have time to make this with divergence, but it matches divergence here. What this is showing is basically a measure of the upper level Kelvin wave strength for each of these Kelvin waves. So this is the Atlantic, this is the Indian Ocean. The colors are different simulations. The dampened ones are down here, the amplified ones are up here, the magenta is the high res. Basically the idea here is that all of these runs at upper levels, we're able to modify them. And you're modifying them more if you actually modify the convection. So if you change the moisture at initialization, you can either dampen or you can amplify the Kelvin wave a lot more, at least in the Indian Ocean. Things are starting to fall apart in the Atlantic Ocean. We actually don't have that. We have a separation between modifying the wind, or the dynamic signature of the Kelvin waves, but you don't have this moisture kind of when you dampen just the wind, you actually somehow dampen the Kelvin wave more. It seems counterintuitive. So this was already kind of a warning flag of what's going on here. But at least we know that generally we're able to modify these Kelvin waves. Now let's look at convection. Convection is the real thing we want to look at because that's what we know might affect other atmospheric things. So now I'm going to show you more complicated figures and then I'm going to break it down in a summary on a later slide. What I'm showing you here is a Hofmahler. So again, we're looking at longitude on the x-axis. Time is increasing as you go down, and this is the Kelvin wave signature right here. So that's the active and the suppressed part of the Kelvin wave. This is a control run. Remember, this is the Indian Ocean. And we have an amplified and a dampened everything run on either side. That contours are actually showing us the difference between the amplified and the control and the dampened and the control. And so one thing that's pretty obvious here is that with the amplified pace, we're actually able to, the positive here is the solid lines, we're able to increase that convective signature. So in the Indian Ocean, if we modify the Kelvin wave, we're able to change its convective signature. And this is again indicating that there is some convective coupling here that we're tapping into. And the opposite true for the dampened to all case. Now, one thing to point out, I call this run the high-res run, but in the Indian Ocean, it's actually not high-res. So it actually looks pretty similar, and it's just slightly higher resolution, but still parameterizes convection. But if you compare this to the I-merge, this is the real data. This is what really happened. I had to use different contours because the Kelvin wave in real life is a lot stronger. But actually it matches the signature, at least the location of the Kelvin wave well. There's a Kelvin wave in the control and these other runs, and it does exist in the I-merge data. But if you just modify the winds, so you don't modify moisture, it's kind of neat. You actually are, this is just looking the same thing, just modifying the winds. You're actually able to change the Kelvin wave. So in this case, we're actually able to dampen the winds, not change anything about moisture. Well, it actually ends up affecting, weakening the convective signature of these waves and vice versa. And this is kind of showing us that there's this delayed impact, but it's kind of implying that there is this coupling. So if you're modifying the dynamics, it's eventually manifested in the convection, even if you don't modify the moisture fields. So that's really neat. So, this method seems to work, right? And then I've been doing this whole talk, you're probably sick of hearing this. And then we get to the Atlantic. Oh, the poor Atlantic. What happens? This is the same color bar as before, showing Kelvin filtered signatures. This is the open Atlantic. There's nothing there. Yeah, there's nothing there. It was very, very sad when I ran these. I thought my PhD was over, honestly. Maybe it still is. So there's no Kelvin wave in the control run. This was shocking, actually, to me. And one thing you see is this is a Pacific Ocean Kelvin wave, not the Atlantic one we're focused on. Well, that one works. So we have a Kelvin wave in the Pacific that propagates into the Atlantic, and we're able to change that, but we have nothing to change in the control, and so nothing really happens. And this is what happens this is what I-merge is supposed to look like. A is what it's supposed to look like. D is what it looks like in the control. Yeah, pretty bad. So the high resolution run actually does simulate a Kelvin wave, but it's a lot different too. So we're able to get the Kelvin wave by having convective, the resolved convection in it, but still kind of off. So kind of takeaway here is what's going on in the Atlantic. And that's kind of what we're gonna focus on for most of the talk. And just to give you a summary of this, I know I showed you these hobblers and maybe it's a little confusing. This is actually just a summary of the filtered rain rate for each of these waves. So in the Indian Ocean, the reds are when we amplify it, the green and yellow when we dampen it. We're able to change the rain rate over time in the Indian Ocean, as I showed you before. In the Atlantic, this is just, the high-res run has a Kelvin wave, and then it's a mess down there. It's the opposite, and actually the amplified case actually the weaker Kelvin convection. So, okay, what's happening in the Atlantic? This was the question I asked myself many times on the verge of tears. But okay, so what's happening in the Atlantic? Well, what we're looking at here are rain rates. So we're looking at the rain rate, looking at time period. Top is I-merge, middle is high-res, controls in the bottom. Projector's not a great place to showcase this, but watch the center open Atlantic region. So the control 30 kilometer versus high-res and I-merge. Okay. Already, you see there's a huge difference in the amount of convection in the intertropical convergence zone, the ITCZ. There's basically none of that in the control. 30 kilometer control has nothing there. So this is a warning sign, but let's quantify that a little bit. So this is looking at the average rain rate, everything, not just the Kelvin. Ending on the 26th, we choose this because this is before the Kelvin wave actually enters this box right here. And all these lines are about the same, except for the I-merge is in the black, the high resolution line, this is in the magenta. So what actually happens is that none of the 30 kilometer runs actually simulate any of this convection, or at least the same magnitude of convection over the open Atlantic. But the high res is somewhat able to, but maybe overdoes it a little bit. If you can, I had a circle coming in. There it is. And the Indian and Pacific Ocean rainfall, this is the same plot, but looking at the Indian and Pacific Ocean. And yeah, there's some differences, but in general, this general structure looks, maybe a little bit more similar, right? This is again kind of qualitative here. So they look kind of similar. And there's always been this temptation to say, okay, well, obviously the high res is going to do better because the high resolution run is going to simulate the convection directly, and that's going to help with the Kelvin wave. But I don't think that doesn't help us here. So what we're looking at here, this is traditional diagnostics. So this is the distribution of rainfall intensity in the Atlantic and the Indian Ocean for the various runs. And the I-merge distribution is here. So this is the log axis. This is more extreme rain rates. This is weaker rain rates. And so, in the Atlantic, when we actually have high res, we have convection turned on, it actually looks like reality. Everything else does not look like reality. I mean, 30 kilometer cannot simulate the extreme rain rates. We kind of knew this. But that doesn't mean, that's not the reason that this probably isn't working, because in the Indian Ocean, well, we're still not able to simulate this, these extreme rain rates. Maybe we're a little better, but it's, this temptation to just blame this just on the resolution of convection may not necessarily be what's going on here. So just a little more evidence for the wackiness of the Atlantic. Wasn't just us, so, not just us. So this is courtesy of Rebecca Emerton at ECMWF. Again, this is, I think, wild. The IFS system really struggled with this event. So this is the IFS filtered Kelvin signals at different initialization times. The 24th is the one that we did for MPAS, right? But let's focus on the 25th and the 26th. And this, the little contours here are actually the Kelvin signature. On the 25th, on the day 4, there is no Kelvin wave, at least in the convective signal. But on the 26th initialization, there is a Kelvin wave. There's like a switch that gets turned on where we're suddenly able to resolve this Kelvin wave 2 days before it interacts with an easterly wave. And not only this, if you look at the rain rates, so I was showing you this box in the open Atlantic, the 40 to 20 west box, and you look at the precipitation. So what we're looking at here is the IFS. You're looking at the IFS, all the ensemble spreads, and the deterministic is plotted here. And it's looking at this day, this box, and basically the rain rates averaged in this box. And IFS is only able to the actual validation is the green here. The IFS is only able to really represent that starting about 2 or 1 day before. So IFS is also not able to simulate this convection out in the Atlantic. And so, a working theory here is that you're not giving the Kelvin wave any convection to effect. I mean, so it's not coupling with convection in the Atlantic. And this is a big deal because, MPAS is supposed to be good at simulating these Kelvin waves, and models, it's not doing it very well. And just to kind of reiterate this point, I ran the simulation where I initialized MPAS on the 26th, which was that magical day. Not magical, but it's the day that the Kelvin wave in IFS actually was able to simulate a Kelvin wave. So this is the control versus the later run, and you get more of a Kelvin wave signature in this, just overall. Now it's still weaker than reality, it's still kind of weird like the high res, but I don't know. I'll take a Kelvin wave over none, I guess. So let's bring this back to some of the original research, and where does this leave us with easterly waves? And this is something that's really kind of future work because we haven't really been able to fully investigate this. Unfortunately, we don't really have a Kelvin wave in the convective signature. We do, I want to reiterate, we do in the Atlantic still have the wind signature in the upper levels of the Kelvin wave. So maybe we still affect the easterly wave. Well, I looked at easterly waves. I looked at all these diagnostics of easterly waves. This is that wave that became Victor. And in particular, I will show you this is the strength compared between simulations. So, what you're supposed to take away here is that it's not much different. So adjusting this Kelvin wave didn't do anything. We didn't adjust the convection, but we did adjust the wind, and it didn't affect the easterly waves. So it doesn't leave me with a lot of confidence that either this method in the Atlantic was able to show us much. Maybe it implies that a theory on convection might be important, but I don't know. It's hard to tell with this. There's this other kind of interesting wave, and I'll leave you kind of with this before we kind of end this. There's this another wave ahead of the wave you're interested in. I call this wave number 2. It's a weaker easterly wave. It also passes Kelvin wave. And I'm just going to highlight what happens. So with this wave, this is the strength of the easterly wave using a metric here. And there's this, dampen everything line. It's a lot stronger in the simulation we dampen everything, and a lot weaker in the simulation we amplify everything. And the wind modification doesn't seem to do anything relative to control. And you may be thinking, well, how could that be? We're not modifying convection in the Atlantic, in the Kelvin wave. Well, we actually kind of are in this case, because what actually happened is that easterly wave originated right here off the coast. And when we modified the initialization, we actually, there was a suppressed Kelvin wave over this area. So what we kind of did is we went and we changed the fields to look more in the amplify case like a suppressed phase, and more like less like a suppressed phase in the dampened. So by dampening it, we're actually adding moisture and removing amplification around the easterly wave. And so maybe you can interpret this as the moisture affecting the easterly wave. But I'm not going to bet on this. I mean, this is just kind of preliminary, hypothesis here. So it could be noise. That's what I said. Let's not read too deeply into this. But I want to kind of bring this back. So I showed you a lot of results, and it seems like kind of a mixed bag. But I actually am really excited about what I showed you today, because what it shows us is that we can modify Kelvin waves at initialization and do something, unless there's no Kelvin wave in the Atlantic, we can change the Kelvin wave's dynamics and its convection. And this gives us hope that there is a way to do some of this attribution work in real models. And it also kind of indirectly shows us this coupling is present in the MPAS simulations everywhere but the Atlantic, right? We also showed that MPAS and IFS, struggle to resolve this Atlantic Kelvin wave. I think it's a real motivating case here. We have this Kelvin wave that we just lose completely, but I think that's actually a really interesting result and something that should motivate follow-up work on this problem. And then we don't really see much in terms of the easterly wave original question, but I think in the future we could we might be able to use a different case and pull something out of this. And I just want to leave you with some, I think, implications, which I kind of talk about. Again, can this modification method address this attributional questions? But really, this is my biggest thing. How common are these low predictability cases? There's not been a systematic study on, Atlantic Kelvin waves and how they're forecast in models. It tends to be kind of this global, analysis, and but we're not looking at individual cases. I think this really motivates that we have to be looking at some of these cases. And I'm trying to understand, is it inherent to the model, the initial conditions, is it regional? I don't think we have a clear idea. And this is important because if we don't have a Kelvin wave in the forecast and we think they affect other things in the atmosphere, well, then how are we actually able to forecast those interactions downstream? And so I'm going to end here and just show you that there's still hope for the Atlantic, believe it or not. I've been trying to amplify a high-res case where we actually have somewhat of a Kelvin wave in the Atlantic, and it works. But we'll see. If this is only out there 4 days, and we'll see. So we might have some hope for the attributional questions for easterly waves in the high-res case. But I'm going to stop there. 11:45 exactly. Go back to takeaways and try to answer any questions or take your scathing criticisms.
Thank you, Quinton. Thank you, everyone, for being here. Dave.
Yeah. Quinton, so towards the end, you showed that the IFS did not reproduce this wave either, except suddenly on the 26th here.
Yeah.
But, so aren't you initializing from?
Yeah.
Okay, so
yeah.
Is it possible that the whole reason that MPAS is not reproducing this particular Kelvin wave is that the IFS, for which case initialization, is not reproducing? And I mean, can't this just be like a bad case, and that there could be other cases where IFS at least has the right information in the initial conditions?
Maybe. I agree. I think that I haven't looked at this. What I want to look at is I want to look at the initial conditions that are put into IFS and see if we see a sudden shift on that boundary. So that's something I want to look at. But yeah, I agree that I think that could be one of the reasons. However, I think that one of the takeaways here is that I don't know if we understand exactly how common this is. I mean, I think this motivates, is this something that commonly happens in IFS or in other models, in our model? Because if it's clearly happening in IFS and our model physics, I guess, maybe didn't change anything in MPAS, then I think that has implications for forecasting. But we don't know what they are. I mean, there's just, no one's really looked at that. But yeah, I agree. I think it could be initialization. That's something I want to look at.
I mean, you could try cases, right? And also other GFS or analysis, right? Those are all possible.
Yeah, I mean, we initially tried, I was originally looking at this Kurt case that I kind of showed in the beginning. So there's some hope that maybe other cases aren't this bad. It motivates follow-up on that. I think this is an important case to highlight, though, because this happening is pretty crazy. So, yeah.
Well,
Great talk. For the Victor case, as we can see in the high-res, we have really vigorous Hurricane Sam right off to the west. And do you think there's any possible, I mean, in reality, obviously, did not destructively, obviously, interfere with the passing Kelvin wave? Do you think that could trip up the modeling at all to have such a strong hurricane in such close proximity?
Yeah, great question, Will. So I think you're well asked if Hurricane Sam, which was also present in these simulations, could have an impact. Absolutely. Something I mentioned here, Dave, you kind of talked about, looking at different cases and stuff. I mean, it's really hard to pick these cases. We ran a case where we initialized a high res on the 25th, and Sam looked completely different, and the wave ahead of the Victor wave looked different, and it completely changed the outcome. So there is some the Kelvin wave, I've always tried to emphasize, is not the most important thing in the Atlantic. It's just one thing happening in the Atlantic. So yeah, I think that could have had an impact on the easterly wave or the Kelvin wave. But at least in this case, it's worth investigating whether Sam, may have had an impact on the Kelvin wave. So yeah, good point.
There's a bit of a follow-up to that question that I have, but the two cases you mentioned where you have genesis through this mechanism, this interaction, were both tropical storms, and I'm wondering if you found any cases where it became a hurricane or a major hurricane.
Yeah, I mean, so they do exist. Kind of the constraining factor here is that this is actually, most of them tend to be old cases, I mean, Victor was 2021, we had Kirk in 2018, they were both weak systems, and the easterly wave tracks that I used to identify some of these cases doesn't do as well in the Caribbean, but also in the Caribbean, these waves can be a bit further removed from the equator, so it's maybe a little harder to look at those cases. So, but yeah, it does happen. One of the motivations for a weaker case is that there's this also question, about, did the Kelvin wave just provide just enough to let it form in the face of hostile conditions? That could be a factor. But yeah, I mean, there are other cases too. They tend to be.
Yeah, Brian.
So you mentioned toward the beginning that MPAS is generally regarded as being good at creating these and modeling it. Why? What about that model is different than other models?
Wow, yeah, that's I actually I can't answer that directly. I think it's a global model, so you get an assist there. But I don't actually know the answer to that question. Some of these studies that showed MPAS as being good have been done in aquaplanets, so you take that maybe with a grain of salt. There have been case studies like I've done. There's a paper in 2021 that showed a really nice Indian Ocean Kelvin wave, but yeah, I don't know why that's the case. It could be just, it could be in part just due to, a lot of MPAS runs tend to use the convective resolving case. Maybe that's the reason, but yeah, I can't answer that directly.
Well, I got two questions, I guess. The first one, kind of follow on, is what do you think could be done if it's not the resolution to improve some of these global models? If you have any early prediction, and do you think that will help improve a lot of the TC genesis forecasts? And then I'll get past the second one after.
Okay. Yeah. What do I think can be done? I don't think we know what the problem is, so I don't know if I can offer a solution. Do I think it improves CC genesis? I actually don't know. I think that's an open question. I think some of the interactions between these Kelvin waves and other features or other equatorial waves are maybe on the margins. So there could be a lot of cases where fixing the Kelvin wave doesn't change the genesis forecast. But I think this just motivates more. This is like such an unknown. I don't think we have good answers to a lot of these questions. And so, one thing I would like to do, or others have been thinking about doing, is like looking at like reforecasts of a ton of cases historically in these models and seeing if we can quantify the predictability of these interactions in a more systematic way. But yeah, I don't know. It could. Maybe it doesn't. I mean, I think with the Kelvin waves are linked to genesis, but I don't know how much fixing their representation is going to do anything but modify the margins. So that makes sense.
Yeah, that sounds great. And my second question, I guess it's kind of multi-part, but they're all super connected, is what happens if a convectively coupled Kelvin wave hits an already formed TC?
Yeah.
And I guess with that, can they affect multiple African easterly waves as they progress? And then do the African easterly waves influence the CCKW or modify it at all?
All great questions. On the TC question, I haven't looked at this directly. So typically tropical cyclones, once they form, they tend to move a bit further away from the equator. So, I haven't looked at this, but I would assume that the impact on tropical cyclones is less as they become more removed from the equator. I would imagine that it could have, if it doesn't have an effect on its growth, it could have an impact in tropical cyclone propagation, because tropical cyclones are, affected by the steering flow. And so Kelvin waves can modify that steering flow. I actually don't know if they affect anything like RI. I tried to look at RI once, and I didn't see much of a relationship, because Kelvin waves, again, they affect on the margins. So already formed TC might be able to resist that. Sorry, remind me of your other
And then
question.
it was just, can they affect multiple /
Yes.
the African easterly waves influence?
Yes, so how they do. So when we built this climatology, I think there are a lot of Kelvin waves that pass 2 or 3 easterly waves. So they can affect multiple easterly waves. And as for the effect of easterly wave back on Kelvin waves, I would assume there is a feedback the other direction, but I don't know. That hasn't really been directly quantified. But given that easterly waves contribute convection, there could be some impact. But again, I don't think we have the answer to that directly.
I have a question from someone who doesn't know this material very well. How much of the variance do any of these two types of waves discussed contribute to the total variance?
To the variance?
Like the total energy or whatever variable we might think about.
Yeah. So the slide I showed earlier. So for rainfall, it's like 5 to 10% of the variability of a region over a climatology. Individual cases, I mean, Kelvin waves. I quantified this for the first paper on this, and in terms of upper level winds, it's a few meters per second in a region. I can't give you a variance quantity of that, but it's enough to be noticeable. It's not like something that without filtering you often see with the naked eye. But in terms of rainfall, it can actually contribute a lot in individual cases. I mean, probably, yeah. So I wish I had numbers for you, but.
What about the other way, the easterly waves, comparatively?
Easterly waves are going to contribute a lot more to the rainfall variability, and locally they're just stronger waves. I mean, at least they're stronger waves in terms of their local effects are more pronounced. Easterly waves are, you can see them with naked eye, but they're also just, they contribute a lot more in the area they're affecting.
Akita.
Yeah, I really love that you're trying to unpack a failure as opposed to finding a successful case. It's just very refreshing. But my question is, you mentioned trying to identify the low predictability cases, or as a group. That seems like a piece of low-hanging fruit. How come that hasn't happened yet? What's the barrier to doing an analysis like that?
Hopefully it's still open for my postdoc proposals I'm putting in. Why hasn't it been done? Well, I think in terms of the importance of Kelvin waves, people have looked a lot at Kelvin waves kind of as a phenomenon collectively, and forecast skill. There's been less focus on individual cases, maybe just out of convenience, but it's harder to pull out individual events. In terms of their impacts on other phenomenon, it's really, some of this work on TCs and Kelvin waves really wasn't kind of accepted until like 10 years ago. So a lot of like the impacts of individual Kelvin waves to individual events haven't really been packed until recently. So I think maybe there was less of a motivation for looking at some of these individual events. It should be noted that tropical cyclones are one thing that Kelvin waves can affect, but they've been linked to like extreme rainfall events around the world. So it's not just tropical cyclones that we should care about. It's also things like, extreme rainfall, or they've even been linked to like Saharan dust outbreaks. There was a paper like 5 or 10 years ago on that. So I just think it's like the impacts on individual waves hasn't really been unpacked until recently, and so the predictability of those individual events was maybe less of a priority.
Are there any questions online?
No. There's only one person online.
Eric, yeah.
Do the Kelvin waves modify the sea surface temperature at all?
Oh man, I should know the answer to this. No, I don't know. Sea surface temperature is such a slow varying variable. I would imagine it doesn't have much of an effect. These Kelvin waves move really fast. They're really quick, and Kelvin waves have alternating phases. So they have convectively active phase, but then that's followed by convectively suppressed phases. So in terms of net impact, if you look at a region, it's going to feel the effect in one phase or the other. I don't know the answer to that question, but I would imagine it would certainly not be as much as atmospheric variables in the atmosphere. But someone's going to come tell me that I'm wrong. So I'll leave it open. Maybe they do. Yeah.
The MPAS is forced with observed SSTs?
MPAS is forced with observed SSTs, but they're non-varying throughout the simulation. It's an 8-day simulation, so the SSTs don't vary over time.
All right. If there are no other questions, thank you again, Quinton. If you're new to Compass, these 1-hour talks are very special because in some cases it's the last Compass talk before the defense. So Quinton, congratulations, and we look forward to
I look forward to unpacking my failures more in a few months.